Alright, so for today we're going to be talking about transformations of logarithms. And transformations are familiar to you based on what we did with the trigonometric transformations and the power transformations. And so the idea here is that we're going to take the logarithm function, and it's going to have an a value, a k value, a d value, and a c value as normal. The a, k, c, and d values all do the same thing that they did before. So remember that the a value stretches or compresses like this. It will also reflect like this if it's negative. The k value stretches and compresses like this and reflect if it's negative. The d value shifts like this, and the c value shifts like this. Okay? And so you have to have a few starting functions. So as before, we would remember that we could start with a cosine or a sine function and then stretch or compress. Or when we were doing power functions, we started with an x to the third or x to the fourth or fifth, stretched, compressed, and so forth. And so this is now the same thing, where we have a particular base on the logarithm. Alright, so you might start with a base 2 logarithm or a base 10 logarithm or something like that. So what I've done here is I've put the starting functions for base 2 and base 10. And so I've made a table of values for a base 2 logarithm where my inputs, I've chosen some special inputs so that I would get whole numbers as my outputs. Here I've got 1, 2, 4, 8, and 16, giving me an output of 0, 1, 2, 3, and 4. Alright, and so just a quick explanation as to why these outputs are the case. Remember, the way logarithms work is if I input a 1 here, then I have to ask myself, what do I need to raise the base of 2 in order to get a 1? Well, I must raise 2 to the 0 in order to get a 1. If I place a 1 here, then what do I need to raise 2 to in order to get a 2? Sorry, if I place a 2 right here, I need to place a 2 right here. So in order to get a 2, I need to raise 2 to the power of 1 to get 2. Here I need to raise 2 to the power of 2 in order to get 4. I need to raise 2 to the power of 3 in order to get 8. I need to raise 2 to the power of 4 in order to get 16, and so forth. Alright, and then they would continue on. Now if I were to graph these points, here's the starting function for y equals log 2 of x. Okay, and so here it is. And now if I were to transform this, let's say I would have an a value and a k and a d and a c value, I would take this and stretch and compress and do things like that. Alright, here's the starting table of values for a log base 10. So I need to raise 10 to the power of 0 to get 1. I need to raise 10 to the power of 1 to get 10. I need to raise 10 to the power of 2 to get 100, and 10 to the power of 4 to get oops, this was supposed to be a 3 here. 10 to the power of 3 in order to get 1,000. And so here I have y equals log 10 of x, or as you'll see it more commonly written, y equals log x without the 10 there. And so now what we're going to do is, now that we know the format for where the transformations appear in the formula, and now that we know a few starting functions, we're going to take and we're going to perform a few transformations, make a graph, get the range, the asymptote, and the x and the y intercepts for a basic logarithm function. Alright, and so that's kind of where we're at. So here's an example question. that you might see on a test. Graph the following log. F of x is equal to 2 log x minus 2. And find its range, its asymptote, its x-intercept, and its y-intercept. Okay? Oh, and find the domain as well. Alright? And so, basically what I would do is I would start with the log base 10 function, because I noticed that I have a base 10 here. And then I would notice that my a value is 2, so that means I'm going to have to stretch it up by 2, and I would notice that my d value is negative 2, and therefore I must shift that way. Okay? So I need to do a stretch and a shift here. And so what I'll do is I'll start with my main log function here. Log of base 10. It's got a dot there. Here's 10, and we'll say here's 100. Here's 1, and here's 2. So there's the basic one right there. And now I notice that basically what I'm going to have to do here is stretch it up by 2. So therefore, remember that every point here needs to be stretched up twice as much. And so what was at 1 now must be at 2. What was at 0 stays at 0. What was at 2 must now be at 4. And so basically here's the stretched function. Like that. Okay? And so there it is, stretched. And then I must also then shift it 2 units. That way. Oops, that way. Okay, and so now this dot will now be at 102, whereas this dot will be at 12. And so if I kind of follow these dots here, this is now at 2 comma 12. Remember, it got shifted up or stretched up by 2, shifted over 2. This dot right here is at 4 comma 102. Okay, this dot right here is at remember it was at 1 0, or sorry, 0 1, no, sorry, 1 0, that's correct. And so now it's at 2 0. Alright. Oh, wait a minute. I've got these backwards here. This is a 12 and a 2. 12 and a 2. And this is a 102 and a 4. I wrote my y's and x's backwards. Silly me. 102, 4. So my y value is actually 4. And my x value has been shifted over. Okay, so notice all of the x values have been shifted over by 2, and all of the y values have been stretched up by 4. Alright, now basically what I want to do is I want to find out the domain. So if we look at these original functions here, they have an asymptote here at y equals 0. Both of them, y equals 0. And this is a vertical asymptote. So all logarithms start with an asymptote at y equals 0. And the only way that the asymptote can be changed is if I have a d value. So something for you to notice here is asymptotes change location only with the addition of a d value. And so basically what this means is, if you were thinking of this asymptote, if I stretch it up, it doesn't change. If I stretch it this way, it doesn't change. If I reflect it this way, it doesn't change. If I reflect it that way, it doesn't change. If I shift it up or down with a c value, it doesn't change. So the only way I can change it is if I shift it left and right. And so, since my d value is -2, therefore my asymptote is at x equals +2. Because note that my new asymptote has been shifted over 2 spaces. Alright? Which, by the way, the range for logarithm functions is all real numbers. This will always be the case for a logarithm. The domain is affected by the d value as well, because note that my domain starts from here and goes over. Alright? And so it starts at x equals 2 and goes up into infinity. And so the domain is x must be greater than, but not equal to 2, because remember 2 is an asymptote, so therefore it's not equal to. So the domain is x is greater than 2. The range is all real numbers, because this graph exists everywhere in the y, because it goes down forever and it goes up forever as well. And now, finding the x and the y intercepts. As always, to find the x-intercept, you set y equal to 0. To find the y-intercept, you set x equal to 0. And that is, for all functions, the easiest way to find x and y intercepts. So what I'm going to do is I'm going to take my function here, and I'm going to set y equal to 0 and x equal to 0. So when x equals, or when y equals 0, I would say 0 is equal to 2 log base 10 of x minus 2. And now I must solve for this function here. Okay, and so now I'm going to have to do some algebra. The algebra here is as follows. I'm going to have to divide by 2, divide by 2. Alright, the algebra is always done the same way. I would start on backwards, or would start on the outside and try and get rid of everything outside of the parentheses first until the logarithm is all by itself. And so I say 0 is equal to log base 10 of x minus 2. And now what I have here is a definition of logarithms. And so remember, I'm trying to find my x-intercept right now. My definition of logarithms says that 10 raised to this power, or 10 to the 0, is equal to x minus 2, or the argument. So basically the definition of logarithm says, what do I need to raise 10 to? 0, in order to get this. So 10 to the 0 is equal to this here. And so I would say that 1 is equal to x minus 2. And now I have to add 2 to both sides. And I would say that my x-intercept is 3. Okay, oops, and I actually should have written a 3 here. Because as you recall, the previous x-intercept was at 1, and I added 2 to this. Remember how I added 2 to each one of these numbers? So there's my x-intercept. Now I'll find the y-intercept. I'll do that on a separate sheet. So in order to find the y-intercept, remember you set x equal to 0. And so you would say y is equal to 2 log x minus 2. And so I would say y is equal to 2 log 10 of 0 minus 2. And we're going to notice something here. Y is equal to 2 log 10 of negative 2. And now, if I basically want to just solve this, notice y is already isolated. So I just want to solve this. I'll place it into the calculator and I'll say 2 times log of negative 2. And we're going to get a domain error in the calculator. And so therefore, if there's a domain error, there is no y-intercept. And let's go back and look at our graph. And that actually makes sense, because notice I have an asymptote here at x equals 2. And if I've got an asymptote here, that implies that this graph never actually will reach the y-intercept. And so therefore, I have no y-intercept. Alright, so we found the x-intercept to be x equals 3. We found the y-intercept to be y is on none. I'll just write none. Okay, and so in the end, it's really a lot of the same stuff we've already been doing. We got to make sure and look at the domain. Remember, the domain and the asymptotes are both affected by the d value. And let's see, the range is always going to be all real numbers. The y and the x-intercepts are found respectively by setting x equal to 0 and y equal to 0. And we can sketch a nice graph. And here, as I said before, are our starting functions for two of the basic ones, log 2 and log 10. And here is the general format for all logarithm functions with a, k, d, and c values that do the same thing that they've always done in this class. Okay, and so there we have transformations of logarithms.